Okay. On that very light-hearted note, let's start with lecture 8.1, fluid system elements. So, you may have noticed that you have a whole class on fluids, and you might be like, so maybe it just needed to be one lecture, right? Like, why are we doing a whole class on it? We're going to cover that in this course in one lecture. Well, that's I'll try to explain why there's a disparity there. So detailed distributed models of fluids, such as the Navier-Stokes equations, which you guys encountered in fluids, I'm sure, last semester, are necessary for understanding many aspects of fluid systems and for guiding their design. For example, a pump or an underwater vehicle would need to have some detailed fluid dynamic models. Okay. However, a great many fluid systems are networks of pipes, tanks, pumps, valves, orifices, and elevation changes. And at the system level, a distributed or a different, not distributed, approach is required. So if you tried to model every single fluid particle or like every little volume of fluid in an entire distributed network of fluid, that would be an incredibly complex model. It would likely be computationally intractable. You wouldn't be able to even use computers to successfully simulate what would happen in such a large model. And more importantly, it's not important what every little volume of fluid does to your system design. If you're trying to say what diameter do I need this pipe to be, or how big should this tank be, what's the maximum height that this tank will fill to in this situation, those sorts of questions can be answered in a simpler way than having to track where every volume of fluid is in the entire system. Okay, where every small volume of fluid goes, which is what a finite element model would do, which is based on the sort of Navier-Stokes complex model. So there's a place for those. If you want to design the shape of an impeller, you're going to want to know how that fluid's moving around, see where you're getting fluid separation, see where you've got a vorticity that develops. You want to see those sorts of things, which requires the Navier-Stokes equations to explore. But when you're looking at okay, I need a system that's got 3 pumps in it and it's got 2 tanks and these pipes, that sort of analysis isn't really going to be helpful. So that's why we learned this technique, which I think, I don't know. I mean, I'm a little bit biased, but I tend to think that these system dynamics techniques are applicable more often than some of those other techniques in engineering practice, because we're often looking at a system design and not the very detailed, designing one part in the system. We're often looking at a system design. But it's something that depends on the application. So they're both valid. They both have their uses. What we're going to look at is a way to approach a system level design. So hopefully that clarifies the difference a little bit. And it's always a judgment call, when you look at a given problem, which technique would make most sense. You have to answer questions like, what am I trying to understand about the system? What am I trying to gain from doing this analysis? And it might be that you need to go with a distributed model, like the Navier-Stokes equations, or you might be able to get away with a system-level model, which usually is a lot easier to go with. So as with electrical and mechanical systems, we can describe fluid systems as consisting of discrete lumped parameter elements. The dynamic models that can be developed from considering these elements are often precisely the right granularity for system-level design, and so that's why they're so useful to us. They'll be able to tell us how much pressure head do we need this pump to be able to provide, for instance. and that would help us to select a pump. If you're designing the pump, you're probably going to need to do a detailed model, but if you're going to use a pump, selecting a pump is a problem that we encounter a lot, and selecting that in a way that's intelligent and not like just, well, I think this one's going to fit. I see a lot of that out in the world, and that's bad. Well, I should say, I don't like it. Don't like it one bit. I feel like this is the right size of pump, and then it isn't. Yeah. Okay, so we now introduce a few lumped parameter elements for modeling fluid systems. Let a volumetric flow rate Q and pressure drop P be input to a port in a fluid element. Since for fluid systems, the power into the element is the product of the volumetric flow rate and the pressure drop, we call Q and P the power flow variables for fluid systems. So those are the two variables. So they're going to be like current and voltage. They're going to be like force and velocity. They're going to be like torque and angular velocity. Those are the power flow variables for a fluid system. Pressure and the volumetric flow rate. We're effectively ignoring a lot of the details of the fluid system, and we're saying, oh, okay, the pressure drop between two locations is important, and the flow rate that goes through that is also important. The fact that there is in like a pipe, the flow rate depends on where you are in the pipe, like cross-sectionally, right? The center of the pipe, the fluid is moving faster than it is at the surface of the pipe where there's contact. We're ignoring that completely. We're just thinking of like average for that cross-section. What is the flow rate? Okay? And same with pressure. We're saying, okay, that's the pressure, but like we're not worried about what the pressure is different from like the top of the pipe to the bottom of the pipe in the cross-section. We're saying, oh, that whole cross-section is at one pressure. So we're thinking about sort of average values for each location in the system. A fluid element has two distinct locations between which its pressure drop is defined. We call a reference pressure ground. Okay, so what do we usually use in a fluid system as the reference pressure? What do we often use? Atmospheric pressure. Atmospheric pressure. Yeah, that's very common to use as the pressure reference. Okay. So we usually use atmosphere to be our ground in a fluid system. Work done on the system over the time interval from 0 to t is defined as being the integral of the power, of course. Therefore, the work done on a fluid system is just the product of Q and P, the volumetric flow rate, and the pressure integrated over time. The pressure momentum is just the integral of the pressure, which is not something that we've seen before. You probably didn't talk about that in your fluids class. It's a parameter kind of like, it's one of those parameters that we don't usually think of as being very physically interesting, so we don't talk about it much. But it arises in a minute. We'll talk about pressure momentum a little bit. And similarly, the volume is just the integral over time of the flow rate, volumetric flow rate, which makes sense. Volume per second is the volumetric flow rate. If you integrate that over time, you're going to get volume. Now we consider two elements that can store energy, called energy storage elements, an element that can dissipate energy to a system's environment, called an energy dissipative element, and two elements that can supply power from outside the system, called source elements. So we introduce first this more complex element that's not as intuitive. So this is the least intuitive of the fluid elements. But I do think that the fluid elements in general are, I think, more intuitive than the mechanical elements. So electronic systems have the most obvious linear graph modeling discrete element values. I think actually fluid is probably second most intuitive, and it's very similar to electrical, and then mechanical is lower than that. And thermal is actually pretty easy, as we'll see. We'll talk about thermal, but it's kind of a weird one. Okay, so when fluid flows through a pipe, it has a momentum associated with it. The more mass, sorry, I forgot my notes, so this might be interesting. We'll see how this goes. When fluid flows through a pipe, it has a momentum associated with it. The more mass, fluid density by its volume, moving in one direction, and the faster it moves, the more momentum it has, right? This is stored kinetic energy. The discrete element we now introduce models this aspect of fluid systems. So we're going to try to model this momentum, this kinetic energy that's built up when you have a bunch of fluid moving in the same direction. So you have like a big pipe, like maybe it's this like huge pipeline that's transporting oil like over hundreds of miles, and there's a whole lot of fluid, and it's all flowing in one direction. Can you imagine like shutting a valve at the end of that pipe? What would happen? Bad things, really, really bad things would happen. The pipe would definitely burst. That's why you don't just slam shut a valve on a pipe when there's some fluid flowing through it. Even like a small pipe that doesn't have a ton of pressure behind it, if you do that, it can burst the pipe. Slowly shutting the valve off is what you want to do. Slamming a valve shut is not what you want to do. It's because of this pressure momentum. It will create this big pressure wave in the pipe. And that's what we're going to try to capture here. We're saying, oh, there's a lot of energy that's stored in that fluid that's all moving at the same direction. So,
isn't that like the fluid hammer or the water hammer where you shut it off and then you can hear the noise of that?
Yeah, so a water hammer is actually there to try, or a fluid hammer is there to try to dissipate that pressure wave. So you'll see them like stick out near the end of the pipe, and if you slam it shut, the valve shut, it helps to dissipate some of that pressure wave that builds up. So a water hammer is ideally there to divert that and not burst the pipe for you. So it's a device that, I mean, depending on how big it is and how well designed it is, it can help when you slam shut a valve. But if you don't have any water hammer there, then you're going to be in big trouble. I mean, still sometimes the water hammer can't handle how much you're gonna ask of it if you slam it shut too quickly. So depends on the system. So yeah, a water hammer is a good like safety check for it so that you don't burst the pipe, but it doesn't always work completely depending on the situation. So yeah, but that's a cool, I mean, actually I have a student who worked on a water hammer design in this class as like a side project thing. It's pretty fun. There's a lot that goes into it. So, yeah, good. So a fluid inertance is what we're going to use to try to model this. So it's defined as an element for which the pressure momentum gamma across it is a monotonic function of the volumetric flow rate Q through it. So gamma is proportional, well, a linear inertance is such that gamma is proportional to Q. So an ideal or linear one, the function is just a linear function. Where I is called the inertance and is typically a function of pipe geometry and fluid properties. This is called the element's constitutive equation because it constitutes what it means to be an inertance. I will constantly call this a fluid inductor because that's the analog with electrical systems. Inertance is just a really hard word to say, and not a super common word either, but it's probably the best word. So, and it's consistent with the textbook, so I try to stick with that. Great. Although there are nonlinear inertances, we can often use a linear model for analysis in some operating regime. The elemental equation for a linear inertance can be found by time differentiating the constitutive equation to obtain. So we would get d gamma dt equals I was just a constant, right? dq dt, which Q is a power flow variable. Gamma is the integral of the pressure power flow variable. So if you take the time derivative of it, you get the pressure back. So we get dq dt equals 1 over I times the pressure. So we call this the elemental equation because it relates the elements' power flow variables Q and P. So what I'm going to do now is do a little derivation of inertance in a pipe. Well, I will in a second. I guess I have this last thing. An inertance stores energy as kinetic energy, right? Making it an energy storage element. The amount of energy it stores depends on the volumetric flow rate it contains. For a linear inertance, that's this. So this is our energy that's stored. Great. The inertance I for a uniform pipe can be derived as follows with reference to the sectioned pipe shown in figure 8.1. So what we've got here is a pipe, and this is when we're typically going to use inertance, is when there's a pipe involved. So if you've got a fluid system, one of the main elements that's going to show up in the fluid system is going to be a pipe, right? It's how you get fluid around from one place to another place. So pipes are everywhere. So coming up with inertance for a pipe is going to be the inertance that we're going to usually see anyway. So that's why we talk about it. It's snowing. Already. Oh no. Yeah. Snow day. No. Yeah.
Okay, back.
So let's derive how much. Oh, I already put in all the equations. I don't have to do it from scratch. Probably good. I haven't looked at this derivation in a year, so I remember how it goes, but whenever you try to do live math in front of people, it never goes great. You always have to go back and, oh no, this was supposed to be that. I dropped this term. Yeah. So good. So for this pipe, so if you look at the cross section of the pipe, I'll zoom in a bit here just to blow this up. So we have a cross sectional area A, density rho of the fluid. We've got a pressure on one side, location at one end of the pipe, another location at the other end of the pipe. We have a pressure, so pressure 2, pressure 1. We have a flow rate that's going through that region, and we're going to take a length of the pipe. So we're going to do this for some length of pipe. Can we define the inertance associated with that? That's what we'll do. So for an incompressible fluid flowing through a pipe of uniform area A and length L, with uniform velocity profile, which is of course a convenient fiction. So we know that the actual velocity profile in the pipe looks something like this, right? Where the velocity at the edges is 0 approximately, and the velocity in the center of the pipe is the maximum. We're going to pretend like it's just uniform, okay?
Yeah.
Because that's the level of granularity we need. Like we're just saying, okay, it's some average value across the pipe, which works okay. But we should recognize that it's limited in some sense too. So, great. An element of fluid obeys Newton's second law, from which several interesting equations can be derived. So we can start with Newton's second law, F equals ma, right? We have the dv dt, meaning the velocity of like a given piece of the fluid. So if we divide both sides by the area, the cross-sectional area of the element. So if we looked at just like the whole element as a particle, I guess, of mass, we could have a force on it, and we could have a velocity of it. But once you try to break that down into a fluid, you start to go by per area, per cross-sectional area, and you divide it by area, and you get the pressure. Okay, the pressure drop across is equal to m over a. M here is, of course, the fluid density times the volume of the fluid, which is the cross-sectional area times the length. The cross-sectional areas cancel. And we can also change the velocity. The velocity is also per area. It's Q over A. So the volumetric flow rate divided by the area gets us down to meters per second, right? So from meters cubed per second in SI units to meters per second. And so you can pull that A out. So rho L over A, dq dt. Solve for dq dt, and you get the relationship between Q and P to be related with this constant of proportionality. So we recognize that this term must be equal to 1 over I, because this is the elemental equation of a fluid inertance, right? So we just identify this term to be 1 over the inertance. So from this last equality, it's clear that for a uniform pipe and the assumptions above, the inertance is just rho L over A. So clearly, long, thin pipes will have more inertance. In fact, we often ignore inertance in modeling a pipe unless it is relatively long and thin. So for short, fat pipes, we don't have a lot of inertance associated with it. But for long, thin pipes, notice the ratio of L over A is in here. So longer, if you get longer and the cross-sectional area goes up, it doesn't change the inertance. But if it gets longer and the cross-sectional area stays the same, the inertance goes up higher and higher, and it becomes more and more important. If the cross-sectional area gets increased but the length stays the same, meaning you make your pipe fatter and fatter, then you don't need to worry about inertance as much. So it's the long, thin pipes that have the most inertance, which a lot of pipes are, relatively long and thin. So that's the inertance elements. Now we'll do fluid capacitors. When fluid is stored in tanks or in pressure vessels, it stores potential energy via its pressure drop. For instance, a tank with a column of fluid will have a pressure drop associated with the height of the column. This is analogous to how an electronic capacitor stores its energy via its voltage. For this reason, we call such fluid elements fluid capacitors. A linear fluid capacitor and capacitance C, with capacitance C, pressure drop P and volume V has the constitutive equation that the volume is proportional to the pressure drop with constant of proportionality C. That's the capacitance. Once again, time differentiating the constitutive equation gives us the elemental equation. So we have dV dt equals C dP dt. And we like to rearrange that to be dP dt equals 1 over C. And then dV dt is what? Power flow variable. So it's the volume time differentiated. The what? Yeah, it's Q. Well, it's Q. because it is the volumetric flow rate. It is in SI units, meters cubed per second, right? So volume is meters cubed. When you time differentiate it, you pick up a 1 over seconds. So make sure this is not, it's an SMU alert. Early closure today at 1 due to weather.
Really?
Good thing I'm recording this lecture. The other classes would not get a lecture today. That's crazy. Wow. Wow. This snow, man. Snow day! Woo! Okay. Wow, okay. Good. Good. Okay. Wasn't expecting that. Fluid capacitors can store energy, making them energy storage elements in fluid potential energy, which for a linear capacitor is 1/2 Cp squared. I would call it a light flurry. It's the mist of snow.
I think they're just worried because it's saying that it's going to continually get worse.
Yeah. Also, I think that there was that very sad thing that happened up at UW on Wednesday. A student slipped and fell and died. Like that. Yeah. Yeah. So like I think that there's a lot of people are being a little extra cautious right now with stuff, which makes sense. It was super sad. It's really sad when a student dies, and especially when it's just like some silly accident like that. Oh, it's terrible. Okay, so fluid resistors. So let's do these. Fluid resistors are defined as elements for which the volumetric flow rate Q through the element is a monotonic function of the pressure drop across it. Okay, linear fluid resistors, which once again we use typically, have constitutive equation, and it turns out elemental equation as well, that the volumetric flow rate Q is proportional to the pressure P across it with constant of proportionality 1 over R, where R is the fluid resistance. So you're seeing that there's a thing that's sort of like an inductor, the inertance for fluid systems. There's a thing that's kind of like the capacitor, the capacitance for a fluid system. And then there's this thing like a resistor, the fluid resistance that we have in fluid systems. So fluid resistors dissipate energy from the system to heat, making them energy dissipative elements. Okay, so these are typically things like orifices, valves. I would say really any pipe, but especially long pipes, so pipes. They're going to dissipate energy as you flow fluid through them. You don't notice a pipe heat up typically, but there is some heat that's generated in a pipe. The reason that you don't notice most pipes heat up, I mean, one of the reasons is that if there's a working fluid inside the fluid, then or inside the pipe, then it's going to dissipate energy or dissipate that heat really easily. So the heat that's generated doesn't seem like it's much, but it can be more significant than we always recognize. So flow rate and pressure drop sources. Fluid sources include pumps, runoff, etc. So that's one of the things that we'll do in the model. It's okay, what would a volumetric flow rate source be, or what would a pressure source be? And sometimes a pump can be modeled as a volumetric flow rate source, and sometimes a pump can be modeled as a pressure source. It just depends on the situation, the type of pump you have, and how it's operating. So an ideal volumetric flow rate source is an element that provides arbitrary energy to a system via an independent of the system volumetric flow rate. The corresponding pressure drop across the element depends on the system. An ideal pressure drop source is an element that provides arbitrary energy to a system via an independent pressure drop. A corresponding volumetric flow rate through the element depends on the system. Real sources, usually pumps, that's like the most common source in a fluid system, cannot be ideal sources, but in some instances can approximate them. More typical is to include a fluid resistor in tandem with an ideal source, as we did with electrical resistors for real electrical sources. Generalized element and variable types. So we did this for mechanical and electrical systems. We'll do that also now for fluid systems. In keeping with the definitions of chapter 1, pressure drop, P, is an across variable, and flow rate, Q, is a through variable. So pressure is like voltage, flow rate, Q, is like current, right? And that's the actually very close analog, right? Like current flows through, fluid flows through at a volumetric flow rate. There's a pressure at, you think of pressure being located at points, and also we're still very used to the fact that pressure is relative to something else. So atmospheric pressure is relative to the atmospheric pressure outside of your system typically. Great. Consequently, the fluid capacitor is considered an A-type energy storage element. The fluid inertance is a T-type energy storage element, and a fluid resistor is a D-type energy dissipative element. Pressure sources are then across variable sources, and volumetric flow rate sources are through variable sources. So let's just look at a schematic of the type of system we would maybe model. So say you've got a flow rate source. Maybe it's maybe you've been working with the civil engineers and they've got some runoff that comes when it rains, and it fills some holding tank, okay? And they want your help in designing like how big the tank should be, maybe, or how long, or how, like what maybe the diameter of the pipe should be, or something else about the system. They want your help because they say, okay, I know how much runoff we tend to get here, but this is a new type of system, and I don't know dynamically if one tank's going to fill up too quickly. Like, we need to make sure we size this correctly. And they're like, I don't know how to do the dynamic model. So they asked the mechanical engineer on staff, can you help me model this? And then you're like, yeah, no problem. So you draw up the schematic and say, okay, you got some runoff that comes in, so some sort of flow source. And you have some holding tank. We'll look at this tank as having, there's the atmospheric pressure up here, right? P atmosphere. And then down here you have a different pressure at the bottom of the tank. You have this whole pressure head in between, right? So that's going to be the pressure of that tank that builds up. So the height of the, say, water in the tank is going to determine how much pressure builds up at the bottom of the tank. And that's the fluid capacitance associated with a tank. And so that's why we've labeled it C1. We're going to model that as being a fluid capacitor. And now my phone's like blowing up. And then we have another tank, so we're going to do something similar to that. There's going to be a pressure drop across this tank, PC2. And we're going to have a pipe that connects them, and that pipe's going to have a resistance associated with it. Most pipes do have a resistance associated with them. It's a pretty reasonable assumption. And a fluid inertance also. We're going to say that it's long and thin. I mean, it's not really given in the problem as being any specific sizes or dimensions, so we don't know how long and how thin it is. But for now, we'll just say, oh, okay, it's a pipe. It might be long enough that we need to consider its inertance as being an important factor. So let's try to model this. Oh, and then we also have a valve through which water exits back out to atmospheric pressure, right? Out here is atmosphere. Again. So we need to draw a linear graph of the system. I think we can do it. I believe in us, okay? So the first node, it's one of the things we'd like to do when we model systems with linear graphs, is we try to draw the nodes first, right? That helps us quite a bit. So let's try to draw the reference node, or the ground, and we're just going to make that the atmospheric pressure. Okay? So wherever there are other pressures in the system, distinct pressures, we are going to want to have a node for that. So like down here at the bottom of this tank, that seems like a reasonable place to have a node. There's a distinct pressure. Atmosphere's up here. There's some pressure down here, so we'll call this maybe node A. I'm going to label them A, B, C, but like we don't usually do this part, but we're going to take this problem a little bit slower because school's going to close, so whatever. And then we've got this pipe in between. There's not really any like distinct place in this pipe that makes sense to like say, okay, there's a distinct pressure here, and we're instead going to look at, I mean, we could split the pipe in half, but there would be no reason to. We might as well just take the pipe as a whole, okay? We aren't interested in what the pressure is halfway through. We're only interested in what the pressure is between this point and the other point, which is also interesting to us because it's at the bottom of another tank, right? So B would be another pressure location that would be interesting. I mean, another one that is potentially interesting is the pressure over here before it goes through this orifice. But is that any different than the pressure at B? No, it's at the same height, so we don't really have any reason to believe it's significantly different. With the approximate ways that we're modeling this stuff, if it's at the same height and it hasn't gone through some resistance, then we probably can model it as having the same pressure. So I see two nodes other than the atmospheric pressure nodes. So node and node. And the C1, so another thing I like to do is do my A-type elements first. Those tend to be the most easy to identify. So the C1 and C2 elements, they both go to atmospheric pressure, right, from A and B. So this would be C1, C1, and C2. Great. What feeds this C1 capacitor? QS, right? The fluid volumetric flow rate source, QS. And now we have a question of signs. I already drew the arrows pointing down here. The sign convention for fluid systems I don't really get into. The only thing that's important is that you draw, you can draw them in any direction you like, except for the source has to be consistent with what direction the physical source is going. So if you're saying when there's positive flow into the system, our pressure is going to build here, that's the direction we need to draw this volumetric flow rate source. If you had a pressure drop, this was like creating some pressure head, it would need to go the other way because we need to go from high pressure to low pressure. Right now we're going in the direction of fluid flow into the capacitor. But pretty much our signs are arbitrary. We just have to go back and interpret them based on what direction we drew them. Just like in a free body diagram, if you drew the force arrow to the right, then when you get a negative number, you know it was actually going to the left, right? So similarly with these arrows, we put them on arbitrarily and then we can adjust. Okay, connecting A and B, so this is our A, this is our B. Connecting A and B is this pipe. And there are essentially two options. You can either put R1 and I in parallel, or you can put them in series, right? I'm going to argue that it makes more sense to put them in series. So it doesn't matter which order, R1 or I, could be I then R1. And the reason I'm going to argue that this is better than going in parallel is that the fluid inertance stores energy in its volumetric flow rate, right? And the volumetric flow rate, when you go through both of these elements in series, is going to be the same for each of them. But if you put them in parallel, it'd be like fluid could go through the resistor separately than it could go through the inertance. And that's not a great model of what is actually going on. And the fluid inertance is not going to have all of that volumetric flow rate in its energy storage, which it really would in reality. So I think that it's a better model to do them in series. And that's one thing to remember if it's not intuitive to you, that when you do pipe modeling, typically the terms should be in series if you have two, like a resistance and an inertance for a pipe. It should be in series. That tends to trip people up on exams. The last one is this R2, which is the resistance created with this valve that allows the fluid to flow out to atmospheric pressure. It drops from the pressure that's in the tank to atmosphere, so it goes from B to P atmosphere. And we have our linear graph, and we're off to the races, right? We could do a full state space model, and we're actually going to do that in an example. So, yeah, but not today. After the snow's gone. Yeah. Snow day! All right.